Hello everyone! If you've ever tried to write a shader for an engine like Unity, Unreal, or GameMaker, you might have had a tough time. But what you might not know is that these engines are doing as much as they can to make this process as easy as possible for you. The engine functions you make use of cover up and abstract the lower level graphics API code that is far more verbose. What is hundreds of lines of code in raw DirectX is only a couple lines of code with Unity's APIs. This is why you might be surprised when you move to a younger engine like Godot, whose abstractions are not yet as high level as the others in regards to shader work. So today, we'll be going over how shaders work at a lower level, how commercial engines make your life easier, and how we can recreate that functionality. So what actually is a graphics engine? A graphics engine is software that takes in stuff like model, texture, lighting information, shader code, as well as any other generic 2D and 3D data and uses it to instruct the GPU to output images to your screen. This process is not a divine act of God, but rather carefully crafted by graphics programmers through the use of APIs that interface with the GPU hardware, such as DirectX, Vulkan, or Metal. These graphics APIs allow us to compile shaders to machine code the GPU understands, manage GPU memory, and control when shaders actually execute. Remember that a shader is just a program that runs on the GPU. Due to the need for maximum performance, these graphics APIs are as low level as they can reasonably be, which unfortunately means the code is very verbose. A simple hello triangle program in Vulkan is over 1,000 lines of code. It is this API code that makes up the graphics engine, but there's just one problem. Not all platforms support all graphics APIs. Windows supports DirectX and Vulkan, but Apple only supports Metal. So if you wanted to make a graphics that can run on both platforms, you must now write two versions of your graphics engine. For hobbyists, this is inconsequential. They can just use whatever API works on their preferred platform. But for commercial engines who want to have multi-platform support for the games customers develop, a solution is necessary. This is generally fixed with an abstraction layer that goes on top of the low-level platform-specific graphics API code. Functions that unify the functionality, but split the specific API code depending on the development platform. Since Unity and Unreal are effectively closed source, we don't really know what's going on in there, but Godot's intermediary abstraction is called the rendering device. With the rendering device, I can do stuff like create a command list for a compute dispatch, and then depending on the desired platform, that function will go to the proper rendering backend behind the scenes for the DirectX or Vulkan code responsible for command lists, so that I, as the user, do not have to write two different versions of my game. As I mentioned at the beginning of the video though, this is about where Godot's abstractions end, while Unity and Unreal go much further with even more abstraction layers, heavily simplifying the amount of code needed to do certain GPU-driven tasks like the aforementioned compute dispatch. In Unity, dispatching a compute shader is a simple one line of code, but in Godot, it's considerably more involved. Unity and Unreal do a lot more than just covering up the low-level graphics API code too. They also provide proprietary shader language wrappers like ShaderLab and ShaderGraph, making it easier for you to write shaders. They also handle the compilation of your shaders automatically, which is something many people take for granted. In my last video, I announced I was moving to Godot, and I am very much missing how easy it was to write and use compute shaders in Unity, so these past few weeks, I've been working on writing my own version of Unity's compute shader abstractions to make it easier for everyone. Before we go over how it all works though, a word from our sponsor. This video has been sponsored by Brilliant. Brilliant is the best way to learn math, data science, and computer science interactively. With topics covering basic algebra to calculus and beyond, Brilliant's comprehensive range of math courses are built for learners of any level, whether you want to brush up on fundamentals or challenge yourself with advanced concepts. I personally use Brilliant whenever I need a quick refresher on math concepts I haven't worked with in a while, and I think it's a great starting point for someone looking to improve their math skills for game development, as it involves a lot of linear algebra. Since shader programming is also essentially just math, a lot of the lessons can be directly applied to shader authoring to create cool, novel effects like fractal rendering. Be sure to try out everything Brilliant has to offer with a free 30-day trial and 20% off an annual plan when you visit brilliant.org/Acerola. or click the link in the description. Thanks so much to Brilliant for sponsoring this video. Even though I am talking about specific engines today, this knowledge is pretty universally applicable because at its core, everything works the same. Unity's compute functionality has 4 crucial components we need to recreate in order to make our lives easier in Godot. First, Unity's compute shaders aren't technically written in HLSL, but rather a custom shader language that looks like HLSL, so we need to identify how this proprietary language works and write an interpreter for it. Second, Unity automatically compiles compute shaders for you, as well as recompiles them automatically when changes are made to the shader code, so we need to write a system for managing shader compilations. Third, Unity heavily abstracts shader memory management, making it very easy to provide shaders with the data they need while managing all of the uniform data caching for you, so we need to write an optimized shader memory manager. Lastly, Unity completely obfuscates the construction of command lists, so ideally, our compute shader abstraction should lie on top of Godot's rendering device layer to simplify the dispatching of compute shaders. We can't write compute shaders without a language to write them in, so it's time to create our own shader language. Let's begin by identifying how a Unity compute shader differs from a normal HLSL one. The first difference is on the very first line. In Unity, we identify the kernel function names directly with a preprocessor directive, but this is absent in the raw HLSL. Why is that the case? A kernel is just the name of the function that is executed when we dispatch the compute shader. It is often desirable to have multiple kernels in one shader file for organizational purposes. For instance, let's consider a simple multipass shader effect like a separable blur. We first blur horizontally, then vertically. This is 2 separate kernels. Because it's 2 separate kernels, it's technically 2 separate compute shaders and requires 2 separate compilations, but there is only 1 line of code difference between the kernels, so it would be quite annoying to have them in separate files. When you're writing low-level graphics API code and are compiling shaders manually, it's pretty easy to have 2 kernels in the same shader file because the shader compiler can take in a name for the entry point function, so you can just compile once, then change the entry point name, then compile again. Unfortunately, problems arise once we begin trying to automate shader compilation, because automation often requires making certain assumptions. How do we know which functions are the kernels? Unity solves this problem with the kernel preprocessor directive in their custom compute shader language. It informs the compiler how many kernels there are and their names, allowing you to have as many compute kernels as you want, all in one file to keep things tidy. The next difference is with the shader uniforms. In raw HLSL, we specify a memory register associated with that variable, but that is absent from the Unity version. We'll go over the specifics of this later when we discuss shader memory management. Unity also has a whole list of other custom preprocessor directives, but I don't really care about any of those. The main thing I want is that kernel directive, because in Godot, the shader compiler assumes the kernel function is named main, so it is not possible to have multiple kernels in one shader file. This means that for some of my more advanced shader effects, I would need 10 plus separate shader files. So let's get started on recreating this preprocessor directive for ourselves. Godot is mainly designed around Vulkan and GLSL, so we will be writing a wrapper for GLSL instead of HLSL like Unity does. Since the Godot compiler already exists, our goal is to identify and interpret the lines of our custom wrapper language and then strip them off or translate them to GLSL such that we are left with a valid shader prepared for compilation. I have here a GLSL version of our simple 2-kernel separable blur from earlier. Because of Godot's shader assumptions, this is not a valid shader file because there is no kernel named main. In order for this shader to work with Godot's compiler, I would have to split it into 2 separate files with 1 kernel named main each. This is a process that should be easy enough to automate, but we're still missing something important, the thread count of the kernel. In the Unity compute shader, each kernel has a line of code before it that tells us how many threads are in a given thread group. In GLSL, this line of code looks like this instead. I don't really like how this line of code is. I prefer how HLSL does it, so I'll be creating an abomination of a shader language by mixing the two. Now that we've decided how our wrapper language will work, it's time to write and interpret it. First, we declare the kernel names at the top of the file and put the desired threads per group on the line before each kernel. We read this file in from disk and iterate through the kernel declarations until none are left while keeping track of the kernel names, and then strip off those lines from the file, otherwise we'll get a syntax error on compilation because #kernel is not valid GLSL. Next, we need to attach the threads per group to the kernel names. We iterate through the file to find the function declaration, then go 1 line back, strip out the thread group information, and associate it with the kernel name. Now that we have all the information we need, it's time to compile the shaders. For each kernel, we take our stripped shader file code, replace the name of the kernel function with main so Godot knows what the entry point is, insert the GLSL code for thread group information, compile it, and we have successfully automated the separation of one shader file into multiple shader files. Now that we can interpret our new compute shader wrapper language, we need to create a system that automatically compiles and manages the shaders in a project like Unity and Unreal does. If you follow the Godot tutorial for a simple compositor effect, you learn how to compile a shader and dispatch it, which is great. What you might not realize at first though is that this shader compilation will occur for every instance of your compositor effect, which is not great. There's never any reason to compile the same shader multiple times, so clearly we do not want our compilation attached to the effect itself to avoid all those duplicates. If we decouple the compilation from the effect, then we can have the compositor effects ask for a compilation of the shader rather than doing that work itself. This shader compiler will be a global singleton that, on startup, will search the Godot project for any shader files and compile them. We know what a file is based on its file extension, so we should decide on the extension we want to use for our new fancy shader language. I'm a narcissist, so I've decided to name it Acerola Compute, or A-Compute for short, so we would call this a A-Compute shader. Not confusing at all. On startup, we search all of the Godot project files for those that have A-Compute as their file extension, and cache their file paths as well as the shader code. Then, we run the files through our A-Compute interpreter, compile each kernel, and store the references to the kernel compilations in a hash table with the file path as the key. Now that the shaders are compiled, each update loop, we check the contents of each file, compare them with the cached shader code, and if it has changed, we recompile the shader and update the references in the hash table. It's a pretty simple concept, but in practice, there's quite a lot of careful bookkeeping with the references and such. The good news is that we have successfully automated shader compilation and runtime recompilation. Now we just need to recreate Unity's CPU-side compute shader quality of life features. If you recall from earlier, Unity compute shaders do not specify a register for the uniform variables, so why do we need to do it in raw HLSL? Technically, we don't have to specify in raw HLSL either. If no register is declared, then the HLSL compiler will choose a register for you automatically. Ultimately, the graphics engine is fully responsible for what data appears in these registers. If we declare a texture uniform variable, then on the CPU, we must ensure that we bind the texture we want at that specific register before the shader executes, regardless of if we have specified a register or let the compiler do it for us. The graphics APIs provide us with the ability to do this with uniform descriptors. They will hold the pointer to the GPU memory where the texture lives, and will also know what register to bind to. An array of uniform descriptions is known as a uniform set. This is how it works in Unity under the hood, but they have graciously covered it all up for us so we don't have to care. Instead of specifying registers in shader code, they make use of another graphics API feature known as shader reflection, which gives us information about the resources a shader needs. That way we don't have to bother with specific registers and can work with what the compiler chose for us. This is why in Unity we bind resources to a shader based on variable name rather than memory register. As far as I'm aware, Godot does not expose shader reflection functionality yet, so we are stuck with manually specifying bindings. Imagine that we have a color correction shader that modifies the exposure and saturation of our image based on the values of two uniform variables in a buffer bound to register 0. Before we dispatch the color correction, we first need to give it the data it needs. We create a uniform buffer that contains our desired exposure and saturation values. When this happens, the buffer is created in GPU memory while the CPU holds a pointer to it. Next, we create a uniform set that holds the pointer to the uniform buffer. This is also created in GPU memory. This uniform set is what is bound to the shader, such that it can find its way to the exposure and saturation values, and the shader can do its thing. But what if we want to change those values? The CPU does not actually have the uniform buffer memory access. The GPU does, so we cannot just change the value directly. Instead, we must free the GPU memory previously declared, recreate the uniform buffers in uniform set, and rebind them. Because this is a lot of work and is also bottlenecked by CPU to GPU memory latency, we would prefer to do this only when we have to. We can ensure we only do it when necessary by keeping a local copy of our uniforms on the CPU. When the desired uniform values change, then we can recreate the GPU side buffers. Otherwise, we use the cached existing uniform buffers. Automatic uniform caching is yet another feature we all take for granted in commercial engines. Without it, our games would be running quite a lot slower while we spend every frame waiting for that data to move from the CPU to the GPU. Now everything is in place to finish up our compute shader abstraction and actually dispatch some compute shaders. Once again, let's compare some code. On the left, we have a script for dispatching a compute shader in Godot. On the right, we have the same thing in Unity. Our goal is to implement a compute shader wrapper class that interfaces with the global shader compiler, handles the shader memory and uniform caching, and can dispatch its associated shader. When it's finished, our Godot script should look about as simple as Unity's. As we decided earlier, our class will be named aCompute. Its constructor will take the file name of the compute shader we want to use. In this example, our file is named blur.acompute, so we pass blur as a string to the constructor. On construction, we pass the file name over to the global shader compiler to retrieve the associated kernel compilations, which we create unique shader pipeline instances with. Now we need member functions to interface with the underlying uniform cache. Our blur shader needs the current viewport texture and a uniform buffer containing the size of the blur. We implement a setTexture function that creates a uniform object attached to the binding provided in the argument list and holds the pointer to the texture. If this pointer has changed since the last time it was set, then we need to update the GPU memory and recreate our uniform buffers. We also implement a setUniformBuffer function that takes in an array of values and caches them locally. If this array has changed since last time, then we recreate the uniform buffer in GPU memory. There are other types of uniform variables, but we don't need them right now. All that's left is to write a dispatch function. We construct a command list to bind the cached uniform set to the desired kernel, then dispatch and close the list so it goes off to the GPU to be executed. With our interface complete, back in the Godot script, we can replace our uniform variable declarations with our aCompute uniform functions, as well as replace the command list with the dispatch function. Now the code looks just as simple as the Unity script. Yay! In addition to writing much less code, we've made life easier by automating shader compilation and abstracting GPU memory management so that it only updates when necessary. There's still plenty of stuff to do and quality of life features to implement like shader include files, but this is where it's at for now. If you'd like to try out aCompute for yourself, the code is available in the description. Please give it a star. If you'd like to support the channel and help me continue making graphics tooling, please check out the Patreon. As always, a huge thank you to all my current patrons. Without your support, I wouldn't be able to, what is it that I do again? Anyways, that's all from me. I hope you have a great rest of your day, and I'll see you next time.